Hey everyone, for exam wrapper 1, I decided to redo problem number 4 from the exam, and the problem originally states, consider a rock climber of mass m equals 60 kilograms who is ascending a vertical wall and stops for a rest by leaning back on her rope as seen in the diagram. The rope has some unknown tension and makes an angle of 31 degrees with the vertical. As the climber rests, the wall exerts a force F of unknown magnitude. This force F points at an angle of 15 degrees above the horizontal as shown in the figure. So the first part of the problem asked us to determine the magnitude of the tension in the rope that is required in order to keep the mountain climber stationary. So our fundamental principle would be the momentum principle, which states that in order for an object to stay in the same position, the net forces acting on it all have to add up to equal 0 newtons. So I went ahead and drew a force diagram here of all the forces that we have, and you have the gravitational force, which points downward and is equal to negative mg, where m is equal to the mass of the climber and g is equal to negative 9.8 meters per second squared. And we have the force of the wall, which points away from the wall with an angle of 15 degrees from the horizontal. And we also have the tension force in the rope, which points away from the climber and upward. And I went ahead and solved for the force of gravity here, which amounted to be negative 588 newtons. For the wall force, I decided to split it up into the two components of it. So you have the x component here and the y component, and you calculate the x component by multiplying the magnitude of the wall force by cosine 15, and it's cosine 15 because your x component is right here, and if you wanted to use a degree, or if you wanted to use the angle, then cosine of 15, which would be the adjacent component to the angle, would indicate the x component. And you do the same for the y component, so you multiply the magnitude of the force of the wall times sine 15 in order to get the y component here. I split the tension force also into the two components, and you have that the x component is equal to the magnitude of the tension force times the sine of 31 in this case, because your x is in the opposite direction of the angle as opposed to being adjacent to it, and you have that the y component is equal to the magnitude of the tension force times cosine of 31. And in the next slide, you'll actually see that the x component will be subtracted as opposed to added to the other forces in the x direction, because the x component in this case is negative. As you can see, in order to get the resultant vector pointing upward, you have to have a negative x value and a positive y value, which will add it up to equal to the tension force. So here, as I was saying, you're subtracting the x component of the tension force. So I went ahead and grouped all the y forces and set them equal to 0, and did the same thing for the x forces. Now, in order to solve for the magnitude of the tension force, we first have to solve for the magnitude of the wall force in terms of the tension force, so that you don't have two unknowns in the equation. So I went ahead and did that using the x component equation. And you have that the magnitude of the wall force is equal to the magnitude of the tension force times the sine of 31 divided by cosine of 15. And you substitute this back into the y component, net force in the y direction equation, and you can see that everything else is now in terms of the tension force. So using that equation, you have to set everything equal to the magnitude of the tension force, which is 588 newtons divided by the cosine of 31 plus sine 31 times tangent 15, and this all amounts to equal 591 newtons, and this is the magnitude of the tension force. The next part of the question asked to determine the magnitude of the wall force required to again keep the mountain climber in the same position. So the same principle repeats, and net forces have to equal 0. In the previous slide, we actually set the magnitude of the wall force equal to the tension force times the sine of 31 divided by cosine of 15, and now since we know the magnitude of the tension force, we can just substitute that back in and solve for the magnitude of the wall force, and this was equal to 315 newtons. The last part of the problem asks to calculate the minimum static coefficient of friction between the climber's shoes and the cliff in order to make sure that this climber stays in the same position. The basic equation for the force of friction is equal to the coefficient of static friction times the normal force. The normal force in this case is the x component of the wall force, and the friction force is equal to the y component of the wall force. And so you can substitute the different components of the wall force in for friction and the normal force, and based on that you can solve for the static friction coefficient. So you have that the static friction coefficient is equal to sine 15 divided by cosine 15, because your for magnitude of the wall force cancels on both sides. And so this was also equal to tangent 15, which is just 0.268, and this is the static coefficient of friction. Thank you for watching.